Hello, AP Physics 1 students, so hopefully you had a chance to look at problem 14. If not, maybe go ahead and give it a read now. This references a carousel, which is a common piece of equipment on a playground. Just in case you're not exactly sure what I'm talking about, here's a photograph of a carousel. Maybe you're familiar with this. Probably when you were a little kid, you played on it the proper way. Maybe as an older kid, you had someone get on it and then try to spin it as quickly as possible to see how long it took for them to fly off or get really, really dizzy, right? All sorts of fun things you can do with this. Maybe this is the real spinning wheel of death, right? Anyway, so we're looking top-down view at our child or our person here who's running and jumping onto the carousel. Alright, so letter A, you want to find the moment of inertia of the carousel alone. It tells you it's a solid disk, so it's really just a matter of picking the right equation from our list of moment of inertia equations. You should have no trouble. Of course, it's going to be 1/2 mr squared. Here I'm calling it IC for moment of inertia of the carousel as opposed to the person, in this case the girl jumping on. Although I realized reading through that I wasn't as careful with my pronouns. At one point it's he, another time it's she. So I guess this is a gender fluid individual. Maybe we'll call them they. Alright. So for letter B, you want to find the magnitude of the girl's angular momentum right before she jumps onto the carousel. So here's where it gets a little bit strange because you're saying, okay, so we have an equation for angular momentum of a point particle, and that's the thing to use here. I mean, clearly this circle is meant to represent the girl who is very small compared to the overall size of the carousel. So we're talking about a point mass, even though she's obviously an extended object, but it doesn't make sense to describe it any other way because she herself is not rotating, but she's rotating about something. What's she rotating about? Well, it's a little bit strange, right? How are we going to calculate this? What angle theta are we talking about? So right now, here she is before she jumps on the carousel. Let's imagine when she jumps right onto the surface of the carousel. So there she is, still with her linear velocity moving forward. Maybe she hasn't quite connected to the carousel surface just yet. So she has a linear momentum going forwards or towards the top of the page here. And then this is the angle between R and P. So where's R? Well, it's from the axis of rotation, that's the center of the carousel, out to where she is located between those positions. So here's the position vector from the center of the carousel out to where she is located. And then theta is the angle between R and P. You know, we didn't exactly specify that in class, but that's always going to be the construction. Every time theta is part of any equation, it always refers back to the two previous vectors. So it's the angle between R and P. And once we draw like this, it should be pretty clear that theta is going to be 90 degrees. Now I should be able to go ahead and calculate. She is one radius away from the center, so it's going to be the 2.2 meters. There's her mass, there's her velocity, and yes, we're using 90 degrees. Now in letter C, so now she jumps onto the carousel, she becomes part of the carousel. Moment of inertia, remember, is like the rotational analog of mass, and it is additive. So the moments of inertia just combine. So the total moment of inertia is the moment of inertia of the carousel, which we've already gotten from part A, plus her moment of inertia. So which equation should we use for her moment of inertia? Well, again, she's not spinning about her own axis. She's meant to represent a point mass with respect to the entire geometry. That equation is just mr squared. So it's the moment of inertia of the carousel plus moment of inertia of the girl. We already have the moment of inertia of the carousel. Her moment of inertia is just going to be mr squared. You should have no trouble getting the combined moment of inertia of 813 kilogram meters squared. So she jumps on, she sort of becomes part of the moving system. They're going to rotate around together, and letter D, you're going to find the combined angular speed of the girl carousel system. And it's an interaction. So hopefully you're thinking this is conservation of angular momentum. There's no net external torque because we're assuming the carousel is moving on a frictionless axis, which is of course not true, but let's just pretend. Now there is an internal torque. If you think about it, when she jumps onto the carousel and becomes part of the system, there has to be something causing them to join together. There's going to be some sort of force causing them to move together. What force would that be? It's going to be a frictional force, right? She's got to have some sort of grip. If this were a perfectly smooth surface, she would just slide right off of it. But there's got to be some sort of friction there, joining them together, providing a torque, slowing her down and speeding it up. And so we're going to do this from a conservation of angular momentum perspective. The carousel has angular momentum to begin with. She has angular momentum to begin with, which we found back in part B, and they're going to combine to a total angular momentum of the system conserved. The carousel is not a point mass, so of course we're going to be using I omega for it. We already calculated her moment of inertia. It's going to be angular momentum as I omega for the combined system, where we're using the combined moment of inertia in I omega. So now just be very, very careful. You're putting all the right numbers in the right places. You should be able to find 0.539 radians per second as the answer. Notice the angular momentum of the carousel beforehand uses just the moment of inertia of the carousel back from part A, the carousel alone. In the after situation, it's the combined moment of inertia we found in part C. If you were to relate this to a collision that we did back in linear momentum, what sort of collision would this be? Hopefully you see they start as separate objects and combine and move off together. This is like a perfectly inelastic collision. This is the rotational version of a perfectly inelastic collision. What happens to kinetic energy in a perfectly inelastic collision, or any inelastic collision? We know there's going to be a loss of kinetic energy, and so in letter E we're going to find the change in kinetic energy of the system. So we're going to find the kinetic energy before and the kinetic energy afterwards. Let's focus on the after first. What sort of kinetic energy is in the system after they interact with each other? She becomes part of the rotating system, so there's only a rotational kinetic energy. So that's just going to be 1/2 I omega squared, but it is I total prime, it is omega prime. Using the subscripts of initial and final, or using the prime notation, that's what's going to save you and making sure you're careful and knowing what goes where. Now, notice what I'm doing here with the parentheses. I'm putting omega prime parentheses squared. It seems like a trivial thing, but trust me on this, this may save you. If you don't use parentheses there, putting the exponent of 2 next to the prime, well, I hope no one's going to think that's an exponent of 12 and do omega to the 12th power, but that's what it's going to look like, right? And so if you instead want to use the subscript f instead of the prime notation, maybe that works better for you, or using parentheses here is good. Also, again, just be very, very careful that you're doing 1/2 I omega squared for kinetic energy, as opposed to I omega for angular momentum. The two equations look an awful lot alike. It's very easy to mix them up. Now, what about the total kinetic energy in the system beforehand? What sort of kinetic energy are we talking about? The carousel is clearly rotating beforehand, so there's a rotational kinetic energy. But don't forget, the girl is running, right? So she has a translational kinetic energy. That's energy, right? Energy is energy, so make sure we account for all of that. So it's going to be 1/2 I omega naught squared, just the carousel, 1/2 mv naught squared, just the girl. Just to give you some checkpoints along the way to make sure things are working out correctly, here are all the numbers put in. Now, of course, you could do this all as just one big calculation, just do delta KE, final minus initial, but I broke it down step by step just so you can see it. And we should be getting 118 joules for the final, 141 joules for the initial, which gives a delta of negative 23 joules.